In this video, I'd like to give a brief introduction to linear approximation, or in other words, we're going to walk through the process of finding the tangent line to a function at a given point. Before I get into the exact how, I'd like to do just a small, fun example about maybe why this might be a thing that we're interested in. So I'd like to introduce you to a man named Art Benjamin. He's a professor at Harvey Mudd. He's fairly well known. He's a mathematician. He's in fact known by Bill Nye. So I've seen Art Benjamin give talks. It seems like Bill Nye has too, and he advertises as a person who can do computations faster than a computer. And as Bill Nye references over here, he can find square roots of 6-digit numbers in just a few seconds very accurately. And Bill Nye attributes this to practice, which is absolutely a part of what Art Benjamin is doing, or in fact all magicians are doing. Art Benjamin deems himself something of a math magician, and he's very good. But I want to give a hint as to one method that we could take this skill that Art Benjamin has and develop it for ourselves. In particular, we were talking about square roots on the previous page. Let's imagine a function f of x, which will be the square root function. What I want to do is introduce a function of my own that I am going to call L of x. It's going to have the form of a line, mx plus b, and what I would like this line L of x to do is I would like it to have precisely the same slope as the function f of x at a specific point. For us, that specific point is going to be a is equal to 25. For Art Benjamin, this might be a very, very large a value, maybe 6 digits or so. So I would like our line to have the same slope as the function f of x at this very specific point. And I would also like my line to be tangent to this curve, which means it should touch the curve at one specific point. And the point that I would like it to touch the curve f of x at is also this very specific x value, which we're now calling a because it's kind of like a fixed point of 25. Well, that process is telling us exactly what we need. Whenever we want to find the equation of a line, we need two things. We need a point on that line, and we need the slope of that line. So what does that work out to here? In general, the point that we want to be on our tangent line, we want it to touch the curve at the point a, f of a. In this specific example, our a value is 25, and our f of a value is the positive square root of 25, which is 5. In order to get the slope of the line, this is where derivatives are going to be useful to us. We'll take our function f of x, which is the square root of x, or x to the 1/2 power. We'll find the general form of its derivative, 1/2 x to the negative 1/2 power, and we will evaluate it at our specific x is equal to a value to find the slope of our function f of x at the specific x value that we're interested in, which is x is equal to 25. So here, when you do this computation, the slope we get for the line that we desire is 1/2 times the square root of 25, or 1/10. Now I'd like to make a small digression to go enter these things into Mathematica, show you some pictures and some things I'd like us to see about tangent lines. Now Mathematica's function for taking square roots is capital SQRT of x, but in order to not have to type that and to match the nomenclature we were using in the slides, let's define a new function, f of x, that's equal to the square root of x. And this definition will enable us to reference f of x later on in the Mathematica document more succinctly. Let's also create a function L of x, where we determined that the slope of this line ought to be 1/10. And then we need a point on this line, and the point we had in mind was 25, 5. So here are my functions f of x and L of x. I make those definitions within Mathematica, and then I can ask Mathematica to do things like maybe plot those two functions together, f of x and L of x, and we're interested in visualizing the fact that these two functions touch just barely when x is equal to 25. So the window perhaps we might like to investigate this function on might go from maybe 20 to 30, 25 smack in the middle. Now note that these two functions are very close together, which is in fact something we'd like to see, but it can be difficult to tell them apart. Let's have Mathematica make a legend for us using the formulas for our function. So Mathematica tells us here that the blue function is f of x and the orange function is our line. And right here at 25, and in fact in a small range around 25, we can't even tell the two functions apart. It's only as we reach the outside edges of this interval that we can start to see a difference between our function and our line. Now the trick here that Art Benjamin is using is that maybe we want to take something like the square root of 26. This is not a beautiful perfect square, and knowing that it's just somewhere in between 5 and 6 by comparing 26 to the values of 25 and 36, the perfect squares that surround it, that would enable us to give a small guess as to what we think the value of the square root of 26 might be. But if we wanted to have a fairly accurate guess, notice that when x is equal to 26, we can't even see a visual difference between our two functions right here. The value of the line and the value of the function are very close. So maybe instead of trying to take the square root of 26, we could ask for L's value of 26 as a decimal, 5.1. If we compare that to the actual value of the square root of 26, 5.09902, we can see just how close these functions are. In fact, we can compute their difference exactly. There's only a 0.0009 difference between these two values. So this gives you a hint as to perhaps what Art Benjamin is doing. He's taking square roots of numbers using a linear approximation for the square root function. And he's getting very, very accurate estimates while not having to do a lot of difficult mental calculation. So just to reiterate those points, here I've shown that exact graph that we had in Mathematica on a larger window, ranging all the way from 0 to 80 now, so that we can see a couple of things. There's absolutely no reason to believe that the value of the line and the value of our function should be near to one another when we stray away from 25. And indeed, the farther away we get from 25 in each direction, the farther away our line and our function become. So in general, it's not as though this line is precisely the same as the curve, and we shouldn't want to make that assumption. However, when we're very near to this point 25 on the curve, the value of the function and the line are incredibly close to one another. And we can use this to make computations simpler. Lines are just about the easiest functions we've ever learned. We learn how to come up with the equations for lines at a very young age, and the calculations for the y value on a line are generally very simple and straightforward. So what we can do is if we want to figure out the value of, say, a complicated function at a particular point, and we're able to come up with a tangent line for that function somewhere near that point, we could use the value on the line as a proxy for the true value of the function. And if we only need a couple of digits of accuracy, we will have gotten those digits of accuracy at a much smaller computational cost. And so this is the real focus of linear approximation, is to replace very complicated functions with very simple functions in order to get a good approximation for that more complicated value.